Okay, so we finished off with this pretty diagram here yesterday afternoon, and we went through and figured all those out, and then did those examples from that sheet. So let's move on. So a little bit more about watts and kilowatts. So we have here energy, W, so that's for a watt, is the ability to do work and is measured in joules for mechanical energy and kilowatt hours for electrical energy. 1 joule of energy is expended in an electric circuit when 1 watt of power is applied to the circuit for 1 second. In other words, a joule is a watt second. The joule is a very small unit of energy, and the practical unit in electrical applications is a kilowatt hour, which is kilowatts times hours. So remember when we talked about this yesterday, a kilowatt or a watt is a measurement of the rate of using energy. It's not a rate. It's not a unit of energy in and of itself. It's the rate of using energy. So without that time component in there, kilowatt by itself doesn't really tell us much. It doesn't tell us how much energy is being used, because we need to know how long we're using that many kilowatts. Yeah, because it's a rate. It's not a discrete value. A joule, however, is a discrete value. Oh, what? Oh, that's a nice pun there, Boney. A joule is a unit of discrete energy. So a joule is an amount of energy, and the amount of energy that a joule is if we have 1 watt for a second. So that's how much energy we're burning if we use energy at a rate of 1 watt for 1 second. So I could say, for example, that it takes X amount of joules to do a certain job. Let's say lift a car 1 meter. I could say that's 89,000 joules required to lift a car 1 meter. But if I wanted to measure that in kilowatts, then I'd have to know how long it took us to move that car, right? So even though I would use the same energy, let's say 89,000 joules to lift the car 1 meter, if I did that in 1 second, that's a shitload more power required than if I did it in 1 minute. It would be 60 times the amount of power required to do the same amount of work in 1 second than in 1 minute, because we're doing it 60 times faster. Does that kind of make sense? I realize that the kind of difference between kilowatts and joules and sort of discrete amounts of energy versus the rate of burning energy and so on and so forth is a little bit obscure. But I think if we think of it in that terms, that power is the amount of energy required to do a task in a certain amount of time, in a certain amount of time. So the faster I do something, the more power I'm going to require to do it. Which is why, if you look at like weightlifting, right? We talk about Olympic lifting, like clean and jerk and snatch. Those are power lifts. Requires a lot of power because I have to move that weight quickly in order to get under it. Whereas if you look at like a deadlift or a squat or something like that, it's not so much power because I can do it slowly. It doesn't matter how fast I do it. So when you talk about rugby players and stuff, they do those kind of Olympic lifts because they require power. They require to expend a lot of energy or create a lot of force in a very short period of time to make a tackle, move somebody backwards, that kind of thing. So that is power versus energy. So energy is a certain the amount of energy required to do a task, and then power is how quickly we can do that, or how quickly we can expend that amount of energy or create that amount of force. Am I making sense? Okay, silence says yes. Yes, let's move on. So here it is here, energy equals power times time. So a watt is, oh, no, that's not right. Watt equals power times time. No, energy equals power times time. Energy cost is kilowatt hours used times the cost per kilowatt hour. Power times time times the cost per kilowatt hour. the power in kilowatt, and the time in hours. So if we're working out the energy cost of something, we need to know how many kilowatt hours we've used times the cost per kilowatt hour. So when you see on your electricity bill, and that'd be a good way to get a little bit of extra understanding of what we're talking about here is to go and have a look at a power bill, because you'll see the amount of kilowatt hours and then the rate or the cost of per kilowatt hour, and that's how they work out your power bill. It's always got to be in kilowatt hours, because you can't, like I said, a kilowatt itself is not a defined unit of energy. It's just a rate of using energy. So without telling me the number of hours, the kilowatt means nothing. So when we measure our electricity costs, it's always in kilowatt hours, and that's the amount of kilowatts we're using times the time. So if I use 2 kilowatts for 1 hour, that's 2 kilowatt hours. If I use 1 kilowatt for 2 hours, that's going to be also 2 kilowatt hours. And then our price of electricity is always going to be given in a dollar value per kilowatt hour. There is a question on the test that you have to work this out, and I have written an example for us to do, which depending on time, we'll see how we go with that. We'll either do it, well, we might do it after we've gone into class, size up our boots. So here's an example of the electrical energy calculation. If a voltage of 230 volts is applied to a resistor, the current flowing in the resistor is 5 amps. So we're at 230 volts, 5 amps. How much power is developed in the resistor? So power is voltage times current. So that would be 230 times 5. And therefore we have 1.15 kilowatts. 1.15 kilowatts. So that's the rate of energy consumption. If the current in example number 1 flows for 3 hours, how much energy is expended? Well, energy equals power times time. Energy equals power times time. So how much energy I'm consuming, then how much discrete amount of energy am I consuming? It's the rate of using the energy times the amount of time that I've used it for. So if our rate of using energy is our power, that's in kilowatts, 1.15. And we've used that for 3 hours. Why on earth have we added 103 in there? What's going on? Yeah, ignore that bit in the middle, 103. All we're worried about here is the amount of power, 1.15, times the time, 3 hours. 1.15 times 3 is 3.45. So it's going to be 3.45 kilowatt hours, 3.45 kilowatt hours. And that's what we will pay for. If that appeared on your power bill, it would be 3.45 kilowatt hours. And whatever your power cost is, 50 cents a kilowatt hour or whatever, so 3.45 times 50 cents. So the kilowatt hour is the unit of energy which electrical energy supply authorities, it's the power company, use as the basis of their charges to consumers. If the cost of energy is 9 cents per kilowatt hour, how much will it cost to operate a 1.5 kilowatt heater for 8 hours? Okay, so let's look. So our energy cost is going to be power times time. That gives us our the amount of energy in kilowatt hours. And then we multiply that by the cost per unit, which is in this case 9 cents per kilowatt hour. That's not a realistic number, by the way. If you're getting 9 cents per kilowatt hour, then use all the power you can, because it's an insanely cheap value. It should, I think it's around 30 cents for most places, I believe, somewhere between 25 and 35 cents per kilowatt hour. Anyway, so our energy cost, power times time times the cost per unit. So it'd be 1.5. That's the amount of power, because it's a 1.5 kilowatt heater. Multiply that by 8, because we're using it for 8 hours. And that gives us our kilowatt hours. So that would be 12 kilowatt hour. And then we multiply that by our energy cost per unit. And then we're going to be paying $0.09, which is 9 cents, $0.09 per kilowatt hour. So 1.5 times 8 is 12 times 0.09 should equal $1.08. So it's going to cost us $1.08 to run our 1.5 kilowatt heater for 8 hours. It's also, remember, that's not real, right? So if you walk out of here and you're thinking, gee, it doesn't cost much to run a heater, That's not true. Our typical power cost is probably going to be about 3 times this. So in real life, your 1.5 kilowatt heater is probably going to cost more like $3 an hour to run. And in fact, most heaters won't be 1.5, they'll be more like 2.5 kilowatts. So in real life, if we're paying something like 25 cents a kilowatt hour to run a 2.5 kilowatt heater, it's going to cost us about 80 cents an hour, give or take. Yeah, about 80 cents an hour. So 8 hours on that heater would be more like $6 something. Okay, horsepower. So we've talked about kilowatts, and a kilowatt is generally how we measure things. So not just the amount of energy, electrical energy consumed, but we would also talk about kilowatts as being the output power of a machine. Previously, we used horsepower. We still talk about horsepower, right? Sometimes we talk about the power of a car in horsepower. So in New Zealand since 1976, horsepower was replaced by watts as the internationally accepted unit of power in both mechanical and electrical machines. Many older electric motors are rated in horsepower. The relationship between these is 1 horsepower equals 746 watts, so 0.746 kilowatts. It's just a simple conversion, simple conversion, in that the horsepower is the old imperial unit, like inches or miles or pounds or whatever. So the kilowatt is the metric equivalent, and so just like we moved from miles to kilometers, pounds to kilograms, whatever, inches to centimeters, we've moved from horsepower to kilowatts. We don't use kilowatts anymore. However, you will from time to time see things measured in horsepower, and so we need to be able to accurately convert those values. So this would come up particularly if you were replacing a motor. If you had an old motor and you look at the nameplate, right? So when we're replacing that motor, we're going to find the nameplate on it, and it should tell us what the power rating is. Obviously, if I'm replacing an old broken motor, I want to get one with an equivalent power rating or bigger, equivalent or bigger. I certainly don't want one smaller, otherwise that motor is probably going to fail. So if that motor had a power rating in horsepower, I need to be able to convert that to the equivalent kilowatt. So when I go to the motor shop, I can say, I want a 2 kilowatt motor, please, or whatever it is. Although in saying that, if you were going to a specialist motor retailer, I'm sure if you told them I want a 4 horsepower motor, that they would be able to figure out what that means. In fact, they would probably know that better than we would. Nevertheless, we need to be able to work out one for the other. If I'm sitting there looking at 2 motors, and this one says 1 horsepower, and my new motor says 0.5 kilowatts, I need to know, is that bigger, smaller, the same? How does it work? So there is a question on this in the test, and all it is simple conversion. One thing I will say about that test is have a look in the question and be certain about what units it is asking you for. Because if your answer is 3,200 watts, and the question is asking you for the answer in kilowatts, and you put 3,200, you're going to get it wrong. That's 3.2 kilowatts. I know it might sound silly. We've talked about this a couple of days ago, but I had a lot of people on the last course who struggled with that sort of stuff, and they couldn't understand why they were getting it wrong when it was the same answer. But if the question says, give the power in kilowatts, then give the power in kilowatts. If the question says, give the power in watts, then you give the power in watts. So we have an example here of converting from horsepower to kilowatts. We have an electric motor that is rated at 1/4 horsepower. What is the power rating in kilowatts? The power rating is 0.25. That's the same as 1/4, right? Times 746, because it's the number of watts per horsepower. And that gives us a value of 186.5 watts, or 0.187. So we've rounded the 6.5 to a 7 here. 0.187 kilowatts. Pretty simple. Any confusion about that? Is anyone still listening? I've got Rangi's here, Raymond's here. I just think for a second, wouldn't that be funny if everyone had thought, oh, I'll just nip off and have a coffee. and then everyone else will still be there, but actually every single person had just wandered off. And I've got at least 3, 4, 5 of you. That's enough. We got all the important people anyway. All right, good. Okay, so then let's have a little look at efficiency. So this is just working out. So again, we're talking about motors generally. We're talking about electric motors. And we need to look at the efficiency. So efficiency is just the ratio of output power to input power. So whatever amount of energy I'm putting in there, how much energy am I getting out? For example, if I was putting in 1 kilowatt of energy and I was only getting 0.5 kilowatts out, I would see that as being reasonably inefficient. Okay, give me a second, team. I've got somebody who keeps trying to call me, so I'll just mute you. I'll be back in a second. Okay, sorry, team. I'm back again. Can you guys hear me again? Yeah. Okay. Cool. Sorry, it was just confirming our time for the safety people to come in and size up our boots. So that will be at 10. It will be at 10. So we'll finish this off real quick, and then we'll shoot in and get that sorted. Okay. So efficiency of our motor. So it's going to be how much energy do I put in, and how much am I going to get out for the amount of energy that I put in. Now, remember, we can measure electrical quantities and also mechanical quantities in kilowatts, right? So when we're talking about the energy input and the energy output, we are actually talking about two different things, even though it will have a kilowatt rating in and a kilowatt rating out. So my kilowatt rating input is the amount of electrical energy that the motor will consume. The kilowatt rating of output is how much mechanical force that motor is going to produce when it turns. Obviously, efficiency is always going to be less than 100%. If you do an efficiency calculation and you get more than 100%, then you've done it wrong. And if you haven't done it wrong, ring me, because we're going to make $1 billion if we've created a machine that that has an efficiency greater than 100%. Because there's always going to be losses in our motor, so we can never get more output than the input that we put in. That makes sense to everybody. I hope that makes sense to everybody. Otherwise, you're a free power conspiracy theorist, and I don't want to know you. Just as a little aside, when I was at Wintec one day, I was just wandering through the workshop. I was quite new there, running the electrical department, and I came across one of the tutors showing his class YouTube videos of free energy machines. You know, these perpetual motion machines and that sort of stuff. And I just watched, and I was like, "What the hell's going on here?" Like, maybe he's just showing them like crazy bullshit on YouTube. And no, it turned out that he believed it, and so I kind of said, "Oh, I don't know if that's the right stuff to be showing our students. That's not really true science. You know, we're here to teach facts, and showing them crazy free energy machines on YouTube, and then saying stuff like, oh, the reason that these aren't out in the world is because government suppresses it and stuff like that." I said, I think it's maybe not stuff that we should be teaching students. And guess what happened? His students ripped into me because they believed every word that he said. They ripped into me and they went, "Oh, you're just you're just one of the non-believers. That's why this technology doesn't exist," and all sorts of crazy stuff, which really made me think even more. We shouldn't be telling this sort of stuff to students in a class, because they will believe every word that we say. That's why they're here. They're here to learn. They believe that we are the experts. And if you start telling students that free energy machines exist, then they will believe you. And when somebody else comes along, like me in that case, and says, "No, this is all bullshit," then they got quite defensive of their tutor, which was an interesting experience for me. I learned something that day. But I will tell you, as your tutor, that free energy machines don't exist. You can never get more energy out than the energy in. Well, what do you mean? What do you mean, Bailey? Good teacher. Good teacher for teaching stuff about conspiracy theories to their class. That's a bit odd. All right, serious question though. So Vin, you say so the COP and aircon are the same as what we're talking about. What do you mean by COP? Abbreviation, but I can't remember off the top of my head.
Of performance.
There's actually you've struck something interesting there, Vin, about air conditioning, because that is kind of goes against the grain of what we're talking here.
Yep, because it goes like aircons are obviously you're going to get a figure more than 100%, can't you?
I don't know. Are you talking, Vin? I can't hear you. All right, I see what you mean, Bailey. Yeah, you must be a good teacher if they all believe you. No, I can't hear you. Hang on. Where is my... Jeez, these things are a bit sometimes, aren't they?
Can you hear me now?
Can you try again now? Try again now, Ben.
What about now?
Right. I can't hear you. Oh, there we go.
Oh, you can hear me.
Yes, now I can hear you.
Okay.
I just, for some reason, my headphones are showing up as 3 different output devices in Teams. So I just had to
okay.
one. There we go. Okay, go. Ask your question again.
Yeah. So aircons have a coefficient of performance.
Yeah.
That's going to go against what you're saying at the moment, because that's going to be more than 100%.
Correct. So I was thinking about that as I was saying this. I was thinking the only time I've ever come across something that's more than 100% efficient is air conditioning. But I thought I'll leave that because it'll just confuse everyone. But since you brought it up, let's talk about that. So when you look at an air conditioning machine, it's going to give you the same as what we're looking at here. It's got an amount of input power and then an amount of output power. So on air conditioner, when we talk about the output power, it's obviously not the force generated by a motor like the example we're looking at here. It's talking about the heat energy output. So the heat energy output is going to be greater than the electrical energy input for air conditioning and refrigeration in general. So how does that work? And why? How can it have an efficiency greater than 1? So the answer is that the input energy for an air conditioner is the amount of electrical energy required to drive the compressor. Is the amount of electrical energy required to drive the compressor. The compressor is the part in a heat pump that is doing the work. In a traditional heater, we just pump power, pump current through a resistor. That's all a heating element is. Same on your stovetop or anything like that. It's just a resistor, and the resistance in that element creates heat, or turns electricity into heat. It just has a high resistance, so the electricity or the current moving through that resistor converts electrical energy into heat, and it's not particularly efficient. When we're talking about an air conditioner, we're not using a resistor to burn electrical energy to create heat. What we're actually doing is using gas as a medium. So gas will be pumped on an air conditioner. If anybody's familiar with it, air conditioning unit, you'll have an indoor and an outdoor unit. So the compressor will compress and pump a gas from the outdoor unit into the indoor unit, and both the indoor and outdoor units have a radiator inside them. So what is happening is that on the outdoor unit, we are we are evaporating a gas, so that the gas in the outdoor unit is at a low pressure. As it evaporates, to change state, for a liquid to change state into a gas, it needs heat. So it's going to draw heat from the outside air into that gas as the gas boils and evaporates, and then that gas will move into the indoor unit where we condense it. So we compress it back into a liquid, and for it to change state from a liquid gas into a liquid, then it's going to release heat, because a liquid has to be, a liquid state of any element has to be cooler than the gas state. So it's going to release heat. So we could talk more about the refrigeration cycle and how air conditioning works one day in the future. It might be easier face-to-face in a classroom. I have done heat pumps and refrigeration quite a bit, so it is something I know about. It's a little bit outside electrical, the core of electrical. It's more into the HVAC guys, but the core of what's happening here, in very simple terms, is that we're moving a gas from inside to outside, and then back from outside to inside. And as that gas moves, it's just exchanging heat. So we're collecting heat from outside and we into the gas, and then we move the gas inside and release that heat on the inside. And then that cool gas goes back outside, grabs more heat, comes back in and releases that heat. So the reason that we get a greater efficiency is we're not actually burning electrical energy. So it's not more efficient, like we're not creating new energy. All we're doing is using electrical energy to power a compressor, and that compressor is what moves the gas inside to outside. And then the gas is doing the work of grabbing heat from outside, moving it to the inside, grabbing heat from the outside, moving it to the inside. And then, of course, if you're familiar with heat pumps, you'll realize that in the summer we use it the opposite, right? So in the winter we use a heat pump to heat our room, and in the summer we use it to cool the room. So all that's happening here is that most modern air conditioners will have a reverse cycle. So then we're just changing it around so that we're collecting heat from the inside and we're moving it to the outside. And so we're going to cool the room. So although it appears that maybe we're getting free energy, what we're doing is actually the only electrical input is just to drive the compressor. And the gas is doing the work of moving heat from inside to outside. So in that case, then you're bang on. We will, if you're just looking at the nameplate of an air conditioning unit or a heat pump. Sorry, when I talk about air conditioners and heat pumps, team, if you're not aware, that's exactly the same thing. It's just two words for the same thing. It will be technically more efficient. The amount of energy that I'm putting in will be less than the amount of heating that I get out. And that's why we use heat pumps, because they're efficiency-wise, they're way better than any other heating option. Although if you ever interested in looking into it, and you think about the efficiency of, say, a 2.5 kilowatt fan heater that you pick up at the warehouse for $30, versus the efficiency of a heat pump that's going to cost you maybe $2,000 to buy it and then have somebody come and install it professionally. Whilst the heat pump will be made way more efficient, it is actually worth doing those sums and figuring out like how long will it take me to make my money back, because that efficiency is only relevant in terms of the amount it costs me to run those two appliances, right? So if one of those things costs you $30 and one of them is $2,000, you got to ask yourself, well, is it more efficient because it cost me a lot to put this thing in? And in fact, if you do those sums, maybe we'll do one in class one time and have a look. But if you do those sums, you will find often that it might take several years for that heat pump to pay itself off. And then you got to ask yourself, well, will I still be living in this house? How long is that heat pump going to last? When do I have to replace it again? If it takes me 5 years to pay for the heat pump in terms of the efficiency gains over using a regular heater, but the heat pump's only going to last 5 years, well, then I've gained nothing, because I've got to then replace it again and I have to start the equation all over. So nobody ever talks about that when we talk about heat pumps. All we talk about is the efficiency. And the reason is, I wouldn't say it's a conspiracy. It sounds like a conspiracy when I say it like this, but the reason that like the government and power companies and so forth want you to use something like a heat pump, want you to use be more efficient on energy, is because it takes the burden off our generating facilities, and therefore we don't have to build new ones or have more or so on and so forth, or cut loads elsewhere. So they want us to use the minimum amount of energy possible, because it cuts down on the burden on the generating facility. So they don't actually care how much it costs you, because that's your cost. They don't give a shit. But they do care about the burden on the electrical grid. So if you would be constantly, we are constantly bombarded with the idea that heat pumps are more efficient and therefore better, and everyone should have a heat pump. But as I say, it's worth doing the sums before you went and invested that amount of money, because you may find that it's not as efficient as you would think when you factor in the total cost of that appliance. Does that answer your question, Vin?
Yeah, that's a fucking pretty long answer, but yeah.
Well, you should know that you can't ask me a question and get a 2-second answer. Yeah. If we're gonna bother answering it, we might as well talk about all of the things around it.
Nah, sure.
All right, cool. Okay, so I think. All right, so we just got one slide to go. Okay, so just the equation for our efficiency here. So it's going to be output power divided by input power. So as it says there in red, always less than 1, unless we're talking about air conditioners, but let's not talk about that for now. If we're just talking about a motor, our output power will always be less than our input power, and therefore output over input will always be less than 1. And then we're just going to multiply that by 100 to get a percentage. So if my output power was or let's say 1, my output power was 1 kilowatt, but my input power was 2 kilowatts. 1 divided by 2 is 0.5. I'll multiply that by 100. 0.5 times 100 is 50. So therefore, my efficiency is 50%, which makes sense, right? If my output power is 1 kilowatt, my input power is 2 kilowatts, I'm only getting half the input power, so my efficiency is 50%. It's pretty simple equation. It's just how to work out a percentage. Just remember, it's always output over input. The answer should be less than 1. If you get an answer more than 1, then you've probably put input and output the wrong way around. Okay, sorry, I don't want to make anyone late. So last slide, and then we get out of here. All right, so reasons for reduced efficiency. So obviously everything by its nature will have an efficiency less than 1, but some things will be more efficient than others, and then some things the efficiency will reduce over time. So if we're finding that our machine is getting a reduced efficiency to what it should have, then we want to have a look at a few of these things here. Friction in the bearings. So, I mean, that's just a general, actually, all of these things here are just general reasons why we would have an efficiency of less than 0, why we will never get 100% output from a motor. Friction in the bearings. So the bearings is what, holds the rotor of our motor. And as it spins, it's going to be, bearings are pretty frictionless. They're designed to be, but there's always going to be some friction. So that friction is going to slow us down and therefore reduce our efficiency. Wind resistance to rotating parts or fans. Often you'll find inside a motor, the rotating part will have a fan attached to it, and that sucks in air and that just helps cool the motor. But obviously the resistance of air, the wind resistance from that fan is going to slightly burden that motor as well, and therefore reduce our efficiency. We'll have an electrical power loss due to current in the windings. So if you think, I've said this lots of times before, anytime we have current flowing in a conductor, then some heat is created. So that heat that we're burning inside the motor, that just by the current running through the windings, is going to burn some of our electrical energy, and therefore we're not getting that energy output. We're putting energy in, burning it as heat, so we reduce our output. And then heat produced by magnetic action in the iron core. We'll cover motors much more later on. I think actually our first look at motors and generators is later on in this module, but I'll tell you that motors operate on magnetic principles. So we're using electricity to create magnetism, and then that magnetism is what's going to spin the motor. So anytime we put power into a coil and create a magnetic field, then we're going to use a little bit of energy in order to create that magnetic field. So again, we're going to lose a little bit of lose a little bit of our efficiency because we change that, we lose that energy. Look, the simplest way to explain this is to remember that just a general principle of physics is that every time I change energy from one type to another, that process will never be 100% efficient, and I will lose some. So in the case of a motor, I'm turning electrical energy into mechanical energy. But all of these things here tell us that there are other types of energy that's going to be created as I do that, and therefore, or there's going to be other types of energy converted. So my electrical energy, for example, the current in the windings is going to turn a little bit of my electrical energy into heat. When I change the electrical energy into magnetism, I'm going to lose a little bit there, because every time I change the energy type, I lose a little bit. So no, I'm not changing 100% of my electrical power into mechanical output force. Some of my electrical power is going to go to friction, heat, magnetism, so on and so forth. Okay, that's the last slide. So we better get into class. Do we have any questions from anybody? No questions. Okay, thanks, Soila. All right, let's end it here. We will go to see those people who need to come in. Those people don't, you can have a rest for a while. Let's start again at 12:30. What we'll do is I've got a little example for us to do on calculation of power costs, because I know that was a question that's given some people trouble in the past. So I've got an example to help us with that. And then we'll move on to the next topic for a couple of hours, and then that'll be us for today. So those people who need to come in, I shall see you shortly. I'm heading that way now. All right.